Hello, this is Andy from the Engineers Academy, and in this video series we're going to be looking at worked solutions to the Unit 1 Engineering Principles exam, which will be sat by students studying BTEC Level 3 Nationals in Engineering. Now, the document that we're going to be referring to today are the sample assessment materials that are or have previously been provided on the Edexcel website, and the document that we're going to be referring to in particular is Issue 1 of the sample assessment materials. Question 17 states the following. This electronic circuit diagram shows a DC power source connected to 3 series capacitors, and the question reads, calculate the total equivalent capacitance of the 3 series capacitors. Now, the easiest way to remember the formulas for capacitors in series and parallel is that they're the opposite way round to resistors in series and parallel. Meaning for this particular circuit here, where we have capacitors in series, our formula is as follows. We have 1 over the total capacitance equals 1 over capacitor 1, 1 over capacitor 2, and 1 over capacitor 3. Now, because all of the capacitors in the circuit have their capacitance in microfarads, we can use those values as they're seen there, providing we remember our final answer is also in microfarads. So what we'll end up with is 1 over CT is 1 over 3 plus 1 over 6 plus 1 over 12. Therefore, 1 over CT equals, running that through our calculators, 0.583 recurring. However, we've not yet calculated CT, because what we'll need to do to get CT on its own is do 1 over that answer. Therefore, CT is 1 over the answer, 0.583 recurring. And once again, I'm going to use the answer function in my calculator so that I don't incur any rounding errors, giving me a total capacitance of 1.714 to 3 decimal places. And recall that our units here are microfarads. So we've completed part A of question 17. Let's move on and look at part B. Now, part B is referring to the same circuit, and it asks us to calculate the charge stored on each capacitor. Well, we have an equation for capacitors that states Q equals CV, or charge equals capacitance times voltage. Now, the important thing with capacitors is that the charge on each of those series capacitors is going to be the same. So what we can actually say is that the charge on capacitors 1, 2 and 3, because they're all the same, equals the total capacitance times the supply voltage. So if we just check on the value of our supply voltage from the question above, we can see that the supply voltage is 240. Well, we've just calculated our total capacitance. So now we can say that Q equals CT times VS, which equals 1.714 microfarads. Well, micro is times 10 to the minus 6. And we've just said there that our voltage is 240. Now, when we run that through our calculators, we get a charge equal to 4.1136 times 10 to the minus 4. Now, charge is measured in coulombs. Now, I would say that this next step is optional because we've got our answer stated correctly there in coulombs. But one thing that I know is that 4.1136 times 10 to the minus 4 is exactly the same as 0.41136 times 10 to the minus 3 coulombs. So I'm going to express my answer in millicoulombs, 0.411 millicoulombs. However, as I mentioned there, I think that's optional. I think you would still get all of the marks if you left the answer in coulombs. Okay, so let's move on. We've answered parts A and B, and now on to part C, which wants us to calculate the total energy stored. Well, the equation for the energy stored in a capacitor is E equals CV squared over 2. Now, because this question wants the total energy, we're going to need to use the total capacitance. So we already have our total capacitance from earlier in the question, 1.714 times 10 to the minus 6. And that answer there is in farads. We know our supply voltage is 240. So we have 240 squared over 2, giving us an energy equal to 0.04936 joules. Now once again, I'm going to express that in millijoules. However, I believe that if you expressed your answer as it's seen there, then you would get all of the marks. But converting this to millijoules, if I times it by 1,000, my answer there is the same as 49.36 millijoules. Now the final step is to calculate the voltage on each capacitor. And one thing we know from previously is that the charge on each capacitor is the same, and we've already calculated that charge earlier in the question. So if we just refer back, we'll make a note of our charge. We have a charge of, seen here, 4.1136 times 10 to the minus 4. And just as a reminder, we have 3 capacitors. We have capacitor 1, which is 3 microfarads. We have capacitor 2, which is 6, and capacitor 3, which is 12. So let's make a note of all of that information down in our working area. So we have a charge equal to 4.1136 times 10 to the minus 4 coulombs. We have capacitor 1, which was 3 microfarads. We have capacitor 2, which was 6 microfarads. And we have capacitor 3, which was 12 microfarads. And we have our equation, which states that Q equals CV. Now we're being asked to calculate the voltage drop across each capacitor. So rearranging that equation, we need to divide each side by C, or the capacitance, and we get V equals Q over C. So let's begin by doing that for capacitor 1. So capacitor 1, the voltage drop is going to be Q over C1. We just need to take a bit of care with our standard form here. So we have V1 equals Q, 4.1136 times 10 to the minus 4 over capacitance 1, which is 3, times 10 to the minus 6. It's times 10 to the minus 6 because we have microfarads. So let's run that through our calculators and we get 137.12. Next, let's move on to capacitor 2 and capacitor 3. So capacitor 2, we're trying to find V2. V2 is going to be the charge, which is the same on each of the capacitors. But this time we need to divide it by the capacitance of capacitor 2, which is 6 times 10 to the minus 6, giving us a value of V2 equal to 68.56. And once again, that's volts. Now finally, we can find the voltage drop across capacitor 3, which is the charge which exists on each of the capacitors, divided by the capacitance of capacitor 3, this time 12 times 10 to the minus 6, giving us a voltage of 34.28. Now once again, this is an optional step, but what we would expect is the total voltage drop to equal our supply voltage. So we could check what we've got there, and we would check it by doing the supply voltage equals V1 plus V2 plus V3. Bearing in mind this question's worth 6 marks, it's probably worth doing this extra step. So V1, we've got 137.12, V2, 68.56, and V3, 34.28, giving us a total of 239.96, or if we disregard any rounding there, that rounds to 240 to the nearest whole number. So I'm satisfied that the values I've calculated there are accurate.